Okay, so welcome to the afternoon session. First talk is by Böttcher, who will be speaking on packing degenerate graphs using pseudorandomness.
Thank you very much. So, in this talk I want to talk about packing problems in graphs and hypergraphs. And what I want to do in the talk is mainly give an overview about what has happened in this very active area in the last few years. And I want to highlight a little bit how pseudorandomness is used along the way to justify that I talk about this in the conference. So let's see. So the journey starts. Oops. Well, okay. I don't want to claim that this is really where the history of this area starts, because there's some controversy and it's not quite clear what happened first and so on. So let me just claim, and I don't want to get into this, so let me just say that my story starts in London, in this ladies and gentlemen's diary in 1850, where Kirkman, who did a lot of mathematics at the time, but he was really a churchman, so he was, so a little bit of an outsider. But he asked the following problem, so that was it's a recreational mathematics journal, and he asked the following problem there. So assume you have 15 young ladies and they should walk to the school, and 3 of them should always go together. So you should group them into groups of 3, and it shouldn't get too boring for them. So on each of the 7 days, they should walk in different groups. Yeah, so, and that was his question. And now in modern language, we call such things Steiner triple systems, although here a little bit more is required, but I will get back to that in a second. So what is a Steiner system in general? So I have some system and I have 3 parameters, t, k, and n. And what I want to start with is an n-element set S. And then I look at each of the t element subsets of this set S. And I want to find a family of now k element subsets, so you should think of t smaller equal than k smaller equal than n, which are often called blocks, such that each of these t element subsets is contained in exactly one of these blocks. Yeah, so here in our example, n would be 15, and the blocks would be of size 3, so k would be 3, and t is simply 2, so no 2 should be there together. Now, as I said, I want to talk about problems in graphs and hypergraphs. So let me immediately translate that to the hypergraph language, which I want to use in the following. Sorry. So in the language of hypergraphs, this ground set S, that would be my set of vertices. And then I would look at the complete T-uniform hypergraph on this set of vertices. So my hyperedges would be these T subsets. And what I want to cover these T subsets with are complete graphs, so complete T-uniform hypergraphs, and I, in short, just say T graphs, with K vertices in each of these complete graphs. Yeah, so that's a Steiner system. And so Kirkman asks, for these particular parameters, does such a thing exist? So does S2315 exist? But he wants a little bit more. So remember, he wants that these schoolgirls are really partitioned into groups of 3 girls. So he somehow wants that once we do this, once we find these complete K graphs, that, and in this case, it's just graphs, complete graphs on 3 vertices, so meaning triangles. And so he wants that once I have all these triangles which should cover my edges, that I can furthermore partition these triangles into some parallel classes. Yeah, so that I have a set of triangles which covers all the vertices, so all these 15 girls, and that is one of my class. And then I have another one, and so on. And this is also what is called a resolvable Steiner system. Okay, and so an area of mathematics which looks a lot at problems of this type is called design theory, and there one can ask more general questions. So let me just answer that. I won't really get much back to that in the rest of the talk. One can ask that I don't just want to cover each element, each of these hyperedges once, but I can cover them s times. So that would give me another parameter. Okay. So that's the problem in general for hypergraphs, and that's a big open problem. It has been a big open problem. And now let's first look at this case of graphs where I don't have hypergraphs but graphs. So meaning that my parameter t here is equal to 2. So Quickman asks for partitions into triangles, and a theorem of Reich-Chaudhuri and Wilson indeed constructs or solves when such Steiner systems exist. So these systems S2, 3n, so again I have a graph and I want to cover with triangles, and moreover it should be resolvable, namely I get this covering of the vertices with triangles, and it exists exactly when n is congruent to 3 modulo 6. So where does this funny condition come from? Well, there are some very obvious divisibility conditions that you need when you want to solve that problem. Yeah? And now here, what are the conditions? Well, first of all, what's the number of edges in your graph? Edge choose 2 should be divisible by 3 because we want to cover, we want to pack, so we want to partition this set of edges into triangles. Moreover, n minus 1 should be even, because now if you look at one particular vertex and then all the triangles which lie in this one vertex, then at the vertex you will see n minus 1 edges, and so n minus 1 should be even because each triangle will use 2 of the edges at this vertex. And then moreover n should be divisible by 3 so that I get these parallel classes, yeah? So that I get a partition into triangles of all these vertices. And now if you translate these conditions back, then you can easily see that that's exactly the same as saying that n is congruent to 3 modulo 6. And in fact, their theorem does not only look at the case when k is equal to 3, but looks at general parameters k. So the case when I want to find when I want to cover the edges of my graph with complete graphs on k vertices, and I want to do that in this resolvable fashion. Okay, so for graphs we understood the situation for a long time, and now the question is, of course, how about more general hypergraphs? And that was really a very difficult problem and open for a very long time. And now what do you do if you have some problem which is difficult and you cannot solve? Well, maybe you first ask some simpler problem. Yeah? And some simpler problem was answered also famously by Rödel. And that kind of weakened the problem a little bit in the sense that we now only ask for near Steiner systems. Meaning we don't want to cover all the hyperedges with complete cliques, but we are allowed to have a small leftover. Yeah? And so in this theorem, when I write this theorem, then I write kn to the t to denote the complete t graph on n vertices. Now what is the theorem? The theorem is that we can partition the edges of this complete t graph into edge disjoint cliques on k vertices for any parameters t and k. Almost, not quite, but almost. There will be some small leftover, which is just a small fraction. So epsilon is just a small constant, bigger than 0, which you can choose as small as you want. And so this leaves a very small fraction of the edges uncovered. So that was in 85, and it's an important theorem, but what was even more important was the method that Rödel invented in order to prove this theorem, which is by now called Rödel-Nibble method. So what is the idea? The idea is, well, maybe we somehow want to use a random process in order to show something like this, because it seemed very difficult to come up with explicit constructions and so on. So let's try to do it randomly. And then the first idea, of course, that you should have is that you want to find these cliques on k vertices in your T graph. And now the first thing you could try is to just select them randomly. And that's exactly what the proof does. The problem is just at some point when you do that, you get stuck. Because at some point when you selected many of them, then they will start to overlap a lot. And of course you want them to be edge disjoint. So that's not good. And then Rödel's idea was, well, let's still do the same thing, but let's from time to time pause and think a little bit. So he proceeds in rounds and does exactly this thing of selecting KKT copies randomly, and but only so long as we don't have many overlaps in these KKT copies. Yeah? So we will have few overlaps, and then at some point we will stop. And okay, we don't want any overlaps, so let's just throw away those KKT copies where we actually have some overlaps in this process, and let's take whatever remains. So that's a perfectly nice selection of these clique copies. But now let's really take them out of the graph. Yeah. So I started with the complete T graph on n vertices, and now I took some edge disjoint KK copies away, and now the hope is that whatever I'm left with, I can repeat this random process again. Yeah, and kind of to make this precise of why can we then repeat this random process again is exactly using some pseudorandomness properties. Yeah, so what Rödel shows is that whenever you do one of your rounds of taking away these KKT copies, then whatever remains will still have nice pseudorandomness properties. So that's the first time that pseudorandomness comes in. But let me not now mention what precisely pseudorandomness means here, but it's a fairly easy formulation of pseudorandomness properties. Okay, so that established this result, and this general proof philosophy has really been useful for many, many other problems in this area, but also in other areas since then, and it will appear a few more times throughout the talk. Okay, so that established that for any uniformity of my hypergraph, we can get these near-Steiner systems. And more generally, just because I mentioned designs at the beginning, more generally you can do the same for designs, meaning where you don't cover edges once, but another fixed number of times. Okay, good. And then it took a very long time until this near solution of the problem could be turned into a full solution of the problem. And that was finally announced by Kivash in, I believe it was 2014, that now the problem can actually be solved. Yeah? So what his theorem says, and that was really a big breakthrough, is that as long as n is large enough, if the obvious divisibility conditions are satisfied. What do I mean by obvious divisibility conditions? Well, I wrote them down here, but basically what you have to do is, so I did this exercise for the triangles of what kind of divisibility conditions one needs, and now you have to do the same thing in the general case. But let me not go into how you get exactly these, but it's not difficult. So these are the obvious conditions that you need in order to get one of these Steiner systems, and his result says that indeed, then you get one. And just one remark now, of course, so his theorem is for large n. We know that we need to have some bound on n, so somehow for small n there's some counterexamples to this. But probably we don't need n quite as large as he gets from his proof. Okay, so we know when these Steiner systems exist. Now what's the main idea of his proof, I will really say less than epsilon about his proof, but so the main idea is to start off from this result about Niersteiner systems from Rödel, and then, well, we can only almost do it, so we should think about what do we now do in order to get from this near result to a full result. And in philosophy, he uses some method which has become very important in combinatorics in the last few years and really been used on many problems, and that's the so-called absorbing method. And again, I don't want to say much about this, and I just want to give you the very basic philosophy. So for these kind of problems that I'm talking about here, this method goes back to some paper of Rödel, Wojcinski and Semmel already, but already in some earlier paper of Krivulevich, some similar methods were used. Okay, so what is the basic philosophy? The basic philosophy is, okay, we somehow have some random process of doing whatever we want to do. In this case, we want to find these disjoint cliques. And at the end, we will have a leftover. So if we know that we have a leftover, then once we are there and we have this leftover, maybe there's not much anymore that we can do. So what we should rather do is preparing for this leftover right at the beginning. So meaning before we start the random process, we somehow find some clever structure that will allow us, and in the end, whatever our leftover will be, to absorb it. And that's why it's called absorbing method, meaning to turn this leftover then together with the clever structure into a perfect covering with these. Yeah, so that's the main philosophy of the absorbing method. And well, Kiva's proof is a very sophisticated variation of this method, and he uses a lot of algebraic structure and so on. But the underlying idea is this, and maybe one other remark I should make is that very recently there was some alternative proof by Glock, Kühnlo, and Osthus of this result, and actually doing a bit more. Using, well, the similar basic philosophy, so also using some absorbing type method, but a very different one, so more combinatorial one. So they somehow do this absorbing in steps, so they do it iteratively. Okay, so we now have at least two proofs of this result. Okay, so meaning we understand when we can, in these hypergraphs, in these complete hypergraphs, cover them with complete cliques. Now, one thing we don't really understand yet in the non-graph case is when we can do it with resolvable Steiner systems. So that is still open, and so far it's not clear how these methods can be used for this. But what I want to spend the rest of the talk about is rather to go away from this setting where we just have complete graphs or complete hypergraphs to more general graphs. Yeah, so that will be what I mainly want to talk about. And for the rest of the talk, I mainly want to focus on graphs, because in this more general setting already there are many things that we don't really understand very well yet. But you could have the same definitions for hypergraphs, and this also has been looked at a little bit. Okay, so let me now state what the more general setting is that I want to look at. So we have some graph G. Now that before used to be our complete hypergraph on n vertices, but now you can take some other graph if you want to. And I just write G for guessed graph. And then I have a family of host graphs, so H1 up to Hk, and I want to pack these into this guessed graph. And what does it mean? It means that we get edge disjoint copies of these host graphs in the guessed graph G. Now here's a picture, for example, if I have these three host graphs that I want to pack into this G. Another way of seeing this definition is what I have to do is just color the edges of this host graph such that each of the colors gives you one of these. So they should be, the copies should be edge disjoint. Sorry. They should be edge disjoint, but of course they can reuse vertices. And they don't have to use all the edges of the guessed graph, but there could be some edges which are left over. Okay? So that's the setting. And I mean, for complete graphs or hypergraphs, it's really just the same thing as we looked at before. And here's one conjecture in this area, which has been around for quite some time and is kind of neat, I find. And that's the so-called tree packing conjecture by Giafas. Now, what does it say? It says, so you want to pack now in the complete graph on n vertices. And what you want to pack is a family of trees. And I really allow you to present any family of trees that you want to me. The only condition that I have is that tree number I should have exactly I vertices. And so maybe I could have left T1 out of here, and T2 is also not so interesting. But okay, so that's the general setup. So you can really come up with any family of trees with this property that you want. And then the conjecture says then I should be able to pack them in the complete graph on n vertices. So here's some example on 6 vertices. And as you see here already, if I do this packing, I use all the edges of my complete graph. Yeah, and that's, of course, not only true in this particular example, but it's true in general, and that's somehow what one could see as a little bit as the magic of this conjecture, is that if you count together the number of the edges in these trees, that's exactly n choose 2. So in other words, what you want is a perfect packing. So perfect packing, we always mean that we really need to use all the edges of our graph. Okay, so that's one conjecture. But there are other similar conjectures in the area, and let me just mention one other one, which has been actually around a little bit longer already. Now, Ringe in 63 already conjectured that if you just give me one tree, and now on n plus 1 vertices, then I can pack 2n plus 1 copies of this tree into the complete graph on 2n plus 1 vertices. Yeah, and if you calculate again, if this would be true, again, you would need a perfect packing in order to do that. And there are some variations on these conjectures, for example, in bipartite graphs, in complete bipartite graphs and so on. Okay, so there are some conjectures about packing trees into complete graphs around. And for a long time, we really didn't know very much on these conjectures, and I will summarize that on a slide in the future a little bit. But this is why somebody called Rosa came up with the following idea and said, well, maybe if somehow these conjectures are hard, in particular, now if we look at this one, then maybe we could introduce something to make our life easier. And his idea basically was that, so how about if we use some symmetry? Would that maybe help us in looking at these questions? And there he invented the notion of a graceful labeling. And there's also a famous conjecture attributed to Rosa in connection with this. And I just want to show you that this also has something to do with these packing problems. Now, what's a graceful labeling? Now, a graceful labeling is a labeling of the vertices of a graph with numbers from 1 up to, well, in this case, if I have a tree, then I have numbers from 1 up to n. And it is graceful if now whenever I look at the labelings that this labeling induces on the edges, so I look at some edge, and what's the labeling induced on the edge? Well, that's simply the difference of the two labels in absolute value. Now, whenever I look at these labels on the edges, then they should all be distinct. Yeah? So that's a graceful labeling. What does it have to do with these with this packing problem that I mentioned before? Well, if I can gracefully label a tree, then I can also pack k copies of this tree, or graph more generally, into the complete graph kk on at least 2 times the number of vertices of my graph minus 1 many vertices. Now, how do I do this? Well, I just start putting one copy. Now, these are the vertices of my complete graph. I didn't put the edges. Now, imagine that they are labeled from 1, 2, 3, and so on. So the first copy I just put it precisely in the way that this labeling suggests to me. Okay, so that's certainly fine. But then the second copy I do exactly the same, but I rotate it by once. And then the third copy I rotate again, and so on and so on. And this property of me having a graceful labeling and that the number of vertices is not too small guarantees to me that I won't use any edge twice. Yeah? So we get a packing of copies of this tree, but we somehow get a very nice packing, a very symmetrical one. Okay. And then the conjecture is, of course, that every tree is graceful. So for every tree, we can find such a label. Good. So now, what was known for this conjecture until relatively recently? So people basically looked at very special families. Now, if you go back to the tree packing conjecture about the families of trees. So already in their original paper, Giafas and Leal, they kind of considered paths and stars, or they considered the case where all the trees in this family, but 2 are stars, so that are very easy cases. And then there were some extensions of these results. Dobson, for example, in some series of papers, looked at what if I try to weaken these conditions a little bit. So if I have trees with small diameters and also have some vertex which basically makes them look like a star. And so there were very isolated results. What maybe was a more general observation was the observation by Blowup. So he said, okay, now let's not be quite so ambitious, but let's just try to pack some of these trees. And then he showed that, well, at least you can pack the first n over square root too many trees in this family by using some density arguments. Now, if you try, and he packs the n over square root 2 smallest of these trees. Now, if you instead try to pack as many of the big trees as you want, that took a lot longer and was only done recently by Pollock and Palmer, who showed that they can pack the roughly 1 over 10 to the n to the 1 over 4 largest trees into the complete graph. Okay. Good, so that's what was done here. Now for this graceful labeling conjecture, I mean the idea was, okay, maybe some symmetry helps us to obtain these packings, but unfortunately it turned out that was even more hopeless. Yeah? So it was really only shown for some very special trees which people gave funny names to. And yeah, so that's all that was known until recently. And I apologize, but I didn't even put references here. Okay, and then a few years ago, we turned to this problem, and we thought, okay, maybe one should kind of replicate what happened in this story about the Steiner systems. Maybe now we should try to use some randomness and some pseudo-randomness in order to get near perfect packings of trees. So meaning we don't want to get a packing of our families of trees in the complete graph on n vertices, but we allow ourselves a little bit more space. So we have an epsilon fraction of vertices more. And the theorem that we could prove is the following. Now, as I said, we don't pack into the complete graph on n vertices, but we pack on the complete graph on 1 plus epsilon times n many vertices. And okay, then we could weaken the conditions that you have in the conjecture a little bit, just because we have this more space. So now we don't need to know so precisely anymore how many vertices each tree has, as long as we know that it has at most n vertices. And then, of course, okay, so not every tree, of course, should be that big, because that would give me too many edges. So I also need a condition on how many edges I have in total. So I have at most as many edges in total as I would have in the complete graph on n vertices. And then, but then we needed another restriction, and that's maybe the most serious restriction in this theorem. We needed that the maximum degree of our trees, which I denote by this delta of Ti, is at most some constant delta. Yeah, but then, then now if you have these conditions, then we were able to pack these trees into the complete graph on 1 plus epsilon times n many vertices. And okay, the proof and the proof technique, they also give some similar result for this Ringel conjecture, which I repeated here. But let me not go into this. So now let me very briefly just say a few things about the proof. So we somehow, so again, the basic philosophy of establishing this theorem was, let's try to use a similar method as for the Steiner system. So we somehow wanted to use some random process. And again, we thought, okay, let's use a Rödel nibble in order to achieve this result. Now in hindsight, kind of from today's perspective, we didn't very well know back then how to do these things. So in the meanwhile, we know a few things how to do the whole story better. But at the time, what did we try to do? Well, so what did we say for the Rödel nibble? We said, okay, we want to, so back then we were embedding these cliques, and we said we want to embed a few of these cliques randomly, and then stop and pause and think. So now here the situation is a bit different because these trees, they can be very big. Yeah? So already now if I try to embed 2 of these trees, there might be, and I do it randomly, then there's some serious overlap, and then it's not so clear what I should do. So then we said, okay, then we somehow apparently need to chop up our trees into smaller bits. And that's precisely what we did. We somehow chopped them up into linearly sized subtrees. And then we kind of tried to run this nibble approach on these subtrees. So embed a few of these subtrees and then stop and take the edges that you used out. Yeah, now, of course, the problem is you need to keep in mind that at the end somehow you need to combine these subtrees together again, because they should in the end form one whole tree. The problem is also, so now when I said earlier about how we embed these cliques, I said, okay, some of the cliques overlap, so we just forget about these cliques. Now this I cannot quite do here, right? Because so now if my trees overlap a little bit, my subtrees overlap a little bit, I don't want to forget about them again because I need them in the end. Yeah, so we somehow need to do something else than just throwing these subtrees out, but we somehow need to repair these random positions of the subtrees. Okay, that was all very vague, and I mainly want to mention it in order to show you what one can actually do better and what one should do differently. But now, one more thing is also for randomly embedding these little trees that I've obtained, we somehow used a very complicated random process, and that's what I kind of tried to summarize on this slide. And you don't really have to read so much. The main message is really we somehow used some complicated random process. So what was the process? The process was somehow, so here we have our little subtree. Now we partition the vertices into its 2 color classes. And then we first embed one color class, which is easy. So we just randomly put it somewhere, which is nice because this one color class will form an independent set. And then we just need to put in the other color class. And we do that randomly as well, but now we have the restriction that if we want to put this vertex randomly, we somehow have to embed it into the neighborhood of these embedded vertices already. Okay, so that was the process. And it was somehow complicated, and it introduced a lot of pain. Why was it so complicated? Well, what we were worried about at the time were dependencies. Yeah, so was really that now if I randomly embed this tree, then, and I would just do it one vertex by one vertex, then it's very dependent where these vertices end up. Yeah? So where this vertex ends up, it somehow depends on this vertex. And it was somehow clear from us that at some point these dependencies should become negligible, but we really didn't know how to analyze that at the time. Yeah? So that's why we somehow did it in a complicated way. Okay, so now in the meantime, after this result, there were really a lot of improvements on this. And the first result in this direction was obtained by Misuti, Rödel, and Schacht, who actually first observed that, so we did this, as I tried to explain, we cut our trees into some linear-sized but small subtrees. And they said, well, actually, one shouldn't do it this way. One should actually cut the tree into much smaller bits. One should cut the tree into constantly sized bits, and then kind of run something like the same idea of doing things randomly and so on. But even for doing things randomly, they said, well, why should we actually, now that we have constant size bits, there's no reason to reinvent the wheel again. But maybe we could rather use these results from Reich, Chautouri, and Wilson about putting small cliques edge disjointly into a complete graph. So we could just reuse this result. And that's their proof idea, to reduce, so to cut the trees into very small bits and then reduce the problem with some extra work to the problem of Reich, Chautouri, and Wilson, to the theorem of Reich, Chautouri, and Wilson. And they observed that if we do it like this, then actually we can embed, we can get a similar result, not just for trees, but actually for a much, much bigger class of graphs. So what's the much bigger class of graphs? It's the class of graphs, so for any non-trivial minor closed family, when you take some graphs there, and they again have bounded degree, then you can obtain the analogous result to the result that I showed you on the last slide. Yeah, so now what does it mean? So why do I write minor closed family here? Well, that's basically because these graph families allow separators. So they allow you to have some good separators. And that's what they want in order to cut up these graphs into small bits. Okay. Good. So that was one result. Then Fäberli and Musset, they observed that, okay, now what do we do if actually we don't just want almost spanning graphs? So what did I mean by almost spanning? Let me go back to this result because it's stated in full here. So here we said all the graphs that I'm embedding are allowed to have most n vertices, and here in the host graph, in the complete graph, I have epsilon n vertices more. So they are only almost spanning, and they cannot cover really all the vertices. And that's what they changed. So they again proved the result where you don't use up all the edges in your packing, so you only have a near perfect packing, but now you are allowed to use all the vertices in your graphs that you're embedding. And then very recently, Färber and Sammuti, they obtained some results now again about trees, so not about these more general graph classes, where they weaken this maximum degree condition. So all this here is for graphs with constant maximum degree, and now they can do some much larger maximum degree, of n over log n if you're almost spanning, and of about n to the 1/6 if you want spanning trees. Okay. And now going back from this bigger maximum degree things, Kim, Kühn, and Ostos and Tjomkin showed now again for bounded degree graphs that actually even this restriction about having separators you don't need, but one can actually do it for any class of bounded degree graphs. Okay. Let me just stay for 1 second with this result. So what this shows is that if we are in this setting of almost perfect packings, then, okay, one can translate the tree packing conjecture to this setting and then get this result. But actually in this setting of obtaining almost perfect packings, we can get much, much stronger packing results. Yeah? So we can really have much more general classes of graphs which we can pack in this scenario. Okay. But now returning to the tree packing conjecture, there recently also there was some breakthrough which builds on this work actually, and I will explain in a second, by Jos, Kim, Kühn, and Ostos. And they now showed that indeed the tree packing conjecture is true as long as n is sufficiently large and my trees have bounded maximum degree. Okay, so now okay, and so this I will talk a little bit more about in a second. Just briefly to mention, to come back to these graceful labelings, that I mentioned earlier, which are kind of stronger than these packing questions. Also here in the setting where we want not graceful labelings, but near graceful labelings. Now, what do I mean? I mean, I told you I want to label my vertices from 1 up to n, such that all the edge labels are different. So now here, you don't allow yourself only labels from 1 up to n, but you allow yourself labels from 1 up to 1 plus epsilon n, so a few labels more. And in this setting, Adamaszak, Ellen, Groschu, and Latke, they could also prove such a result, and even for high maximum degree of the trees, so maximum degree n over log n. Okay, so now let's get back to this breakthrough result by Hughes, Kim, Kuhn, and Osthus. How do they prove this result? Now they start off by showing something which is called a Blowup Lemma in the packing setting. And they combine that with, again, some absorbing technique. So I won't say anything about the absorbing technique, but let me tell you just very briefly what a Blowup Lemma is. Now here we come to, again, to some different notion of very weak pseudo-randomness, which is called regularity. And I was a bit lazy, I didn't even write down the formal definition of regularity. But in the next talk, in Maya's talk, she will, I think, do things a little bit more carefully than I do here. So now what's an epsilon regular pair? So it's a bipartite graph where I have that whenever I choose a linearly sized subset in one of the partition classes and one in the other partition class, then the density of the edges that I see here is very close to the density of edges that I see in the whole graph. Yeah, so somehow the edges are quite uniformly distributed, and that is what is an epsilon regular pair. Now, why are these objects nice and important? They're nice and important because Semmelweis regularity lemma tells us that we can partition every graph into objects of this kind. Yeah? And that's maybe all that I want to say about them. Now, what is a Blowup Lemma? Well, the Blowup Lemma says that if we have such an epsilon regular pair, and okay, we need one more additional condition, that's why it's now called super regular, and that just says that each vertex here should see should have a not too small degree. Okay, so now if I have such an epsilon regular pair with some condition on the degrees, then the Blowup Lemma by Komno, Sarkozy, and Semmelweis tells me that actually that's very nice for embedding copies of graphs. So now in this setting, just one copy of graph. And indeed, they can embed any bipartite graph H, which is compatible with this regular pair in the sense that the number of vertices that I want to embed here is precisely the number of vertices that I have here, and they're the same. So it is a spanning graph, and this graph should have maximum degree at most delta. Yeah, but under these restrictions, I can really embed this spanning subgraph inside any such epsilon d superregular pair. Okay, and now what was shown for this solution of maximum degree tree packing conjecture was an analogous result for not putting just one copy, but putting many copies, and namely putting so many that I get actually a near perfect packing. Okay. Good, so that's how they obtained this. We recently now returned to the question and kind of wanted to ask again, yes, fine, but how do we obtain packings or near perfect packings for graphs with bigger maximum degree? So again, here the main restriction was that the maximum degree is bounded by some constant. Yeah, and now of course the question is, how do we get rid of this constant? And we also kind of returned to our methods that we had used earlier already, and kind of wanted to say, okay, we had this complicated random process. It would be really nice to replace it by a much simpler random process. And now that's and the simpler random process, that's what I want to show you on this page. So somehow some very nature random process, but As I said, because of dependencies, we didn't know how to analyze such things at the time, but now we are maybe a little bit wiser or something. So what would actually be, so now if you give me some guessed graphs, G1 up to GT, and I want to pack them into H, what would be the most natural way to do it? Well, somehow the most natural way to do it is, and I somehow want to do it randomly, is, okay, I first embed G1, then I embed G2, and then I embed G3, and so on. And while I do this random embedding, whenever I embed an edge, I really take out this edge, because I don't want to use it again. Okay, so now when I embed my ith graph in this sequence, then I just choose some order in which I want to embed the vertices, and that usually should satisfy some conditions, but okay, you are free to choose the order that you want, which is nice for you. And then I just embed vertex by vertex. So I embed my first vertex somewhere randomly. Now the second vertex, I mean, if it has an edge to this first vertex, I cannot embed it anywhere, but I have to embed it in the neighborhood of this vertex. Okay, but so I just look at the neighborhood of this vertex here, and I embed it randomly into this neighborhood. And then I just continue in this way. So third vertex, I embed randomly into this neighborhood. This vertex maybe doesn't have any neighbors there, so I can again embed it randomly, but of course I shouldn't embed it on anything that I used before already. So I should embed it randomly on whatever remains. Next one the same. And now again, maybe I have some vertex which already has 3 embedded neighbors. So what do I need to do is I need to look at the common neighborhood in the host graph of these 3 vertices. They will give me a set, and there again I embed it randomly. And that's what I do. And then I just continue. At some point I'm done with this copy of this GI, and then I continue with the next graph and so on. So I do it randomly. I never reuse any edges. I take care that my embeddings are really proper embeddings. So when I embed the red graph, I don't reuse any vertices. But under these restrictions, I do it randomly. And what would the hope be? The hope would be, after I did it for some copies of GI, then somehow, now of course I cannot reuse these edges anymore that I used already, so you could think about them as being deleted. And the hope would now be that what I'm left with is somehow quasi-random in some sense. Yeah? So similarly as in this Rödel proof. So that then I can still repeat my random process. Yeah, so somehow we would need to show that such a random process preserves some suitable quasi-randomness property. Okay, so, and now very recently, using exactly an approach like this, we managed to prove the following near-perfect packing theorem together with Ellen Latke and PG, where we look at a very general class of graphs, so-called degenerate graphs. Now when is a graph degenerate? The graph is degenerate if I can order the vertices from x1 up to xn, such that now whenever I look at the ith vertex in this order and only look at the neighbors that it has to vertices which came before in the order. So I only look at vertices x1 up to xi minus 1. And there it has at most d neighbors. And you should think of d as a constant. Yeah, but on the other side in the ordering, it can have as many neighbors as it wants. So that's a degenerate graph. And now we pack families of these degenerate graphs with rather high maximum degree. So we allow maximum degree up to some small constant times n divided by log n. So that's what we want to pack. These graphs are now allowed to be spanning, so we pack in the complete graph, and they are allowed to have n vertices. But again, it's only an almost perfect packing. So the number of edges that we are allowed to have in total needs to be an epsilon fraction less than the total number of edges that I have in Kn. Yeah? But under these conditions, and again under the condition that my n is large, we can pack these graphs. So this now covers really more general class of graphs than all the previous near perfect packing results. And what we use in order to prove this is exactly this random process that I showed you on the last slide. So we use this natural random packing process to pack almost spanning graphs. And then we need to show that throughout this process we somehow preserve quasi-randomness. Now, what's the quasi-randomness property that we use in our proof? Well, it's as follows. So whenever we take a set of vertices in our graph of a certain size L, where L is some constant, and now we look at the common neighbors of these as vertices in the graph, then that should be very close to what one expects. Yeah, so P is the density of the graph, so that's how many, so I have in total P times n choose too many edges. And so that's the number of common neighbors that I would expect, P to the S times n, and I'm very close to this expected number. So that's the quasi-randomness notion that we use. Now, why is this natural? Now, if you think back of our process, I said, for example, at this point, I want to embed this vertex in the common neighborhood of these three vertices. Yeah, and then it would be really nice if I have some information about the common neighborhood of these three vertices throughout my process. And that's what this quasi-randomness notion provides me with. Okay. Now, but that's not quite enough. We need a little bit more. So what we also show is that now when we embed one of our graphs, then these common neighborhoods, so this tells me something about the common neighborhoods in my host graph throughout the packing problem. But now I have this other problem that when I embed one graph, here is my guess graph, and maybe it has nice pseudo-randomness properties in the sense that I know that the common neighborhood of these three vertices is nice and big. And now when I come and I embed my current graph here at the moment, it could be that I embedded already some vertex here, embedded some vertex here, embedded some vertex here, and later I want to embed some common neighbor of these three vertices. Yeah, but maybe in the meantime, before I come to the embedding of this common neighbor, a lot of more embeddings happen, and it could happen to me that I eat up this common neighborhood by these other random embeddings. And that would be bad, because then I would come and I wouldn't have a place anymore to put the common neighbor. So that's something we need to show in addition, that this doesn't happen, that these common neighborhoods are eaten up kind of fairly. So they are all eaten up in the same ratio. Yeah? So when I'm not at the very end of the process, then I will still have some vertices left in each of these common neighborhoods.
So in the proof you use this L only up to D, or do you need for some?
We need a little bit more than D, but maybe 2D plus 1, something like this, but for some technical reasons. But, I mean, that is actually a good point. So you don't want to use whatever this L is in order to show this property, because then somehow your L would blow up. Yeah, so you need to stop somewhere. It's not precisely D, but it's something like 2D. Okay, and then one thing we need to do when we do this embedding, so as I told you a few years earlier, we were frightened of these dependencies, so we somehow now need to control these dependencies. But we now have tools in order to control what I call sequential dependencies. So what do I mean? Well, I mean that if I embed one of the trees, then of course where some later vertices end up mildly depends on where I put some earlier vertices. Okay, and we do this random process not. So I lied here a little bit. So we don't do this random process for the whole graphs that we want to embed, because remember we want to get spanning graphs that we want to embed, but we only do it for some almost spanning fraction of the graphs. And then at the end, of course, we have to extend that to get really spanning copies. But how do we do that? Well, we take away some vertices at the beginning, and then at the end we use some matching argument in order to extend to the spanning graphs. Okay, but that's maybe rather technical, so let me not say that. So I have one more slide which is about these sequential dependencies, but let me maybe not even spell out this horrible lemma because it's already 3 o'clock in the afternoon and maybe it gets a little bit too much. Let me just say that we can develop, we developed tools, and actually in some earlier papers, like for example this near graceful labeling papers, some similar methods have been developed in order to handle these dependencies now. And so we have some lemmas which precisely apply to this situation that we have some random process which somehow proceeds randomly, but whatever happened in the past mildly influences what happens in the future. And the trick really just is to go back to some known martingale inequalities, and in this case we go back to Friedman's martingale inequality. And I mean, that's what one should do. That was clear to us a few years ago, but we just didn't know the right tools at the time. And now it turns out it is not actually so difficult, and it was probably more our fear of the dependencies than anything else that kept us from doing it. Okay, but let me not mention the details of this. Let me rather come to concluding remarks. So for obtaining our new result, we use this, what I call natural random packing process. And the nice thing about this process is that it's a very simple process. So I think it should actually be powerful. And one hope would be, but this is not clear at all at the moment, is that this can maybe at some point somehow be combined with some, for example, some iterative absorption method or some other absorption method in order to actually get some perfect packing. Yeah, so this is, in the result about the perfect packing result concerning the tree packing conjecture that I showed you, the main restriction was that we can only handle trees with constant maximum degree, and now the question is really how does one get away from that? Our packing process can do relatively large degrees. I mean, there's still this barrier at n over log n, but okay, at least we can do that large degrees. Maybe one could at some point combine it with some similar absorption techniques in order to get perfect packing results in that setting. That would be very nice. Why would it be very nice? Well, I mean, having this perfect packing result for trees of constant maximum degree is already great, considering that we didn't know much until a few years ago. But most trees actually don't have constant maximum degree. So a random tree, for example, has maximum degree of the order log n. So doing something with maximum degrees of order n over log n would already be great, because at least it would cover most trees that are out there. Okay, then of course the question would be, how about very high degrees? I mean, both in the near perfect packing as well as in the perfect packing. Then how could I handle vertex degrees which are even higher? And then the next question would be, how about hypergraph versions of all these packing results, where not much is known so far yet. And that would have getting some serious results there, that would be really nice. And it could have some applications towards getting these resolvable designs, kind of thinking in the very long run. Okay, so that's that, and that's just a very tight packing of trees or more general objects, and many thanks.
Okay, so it's time for questions. Any questions?
Yes.
So you mentioned that most of these results are done by natural random packing, but you briefly mentioned also this near graceful conjecture. So this is also?
It's also a random process. So I mean, it's a different random process, because you have to do something different, and you have to be, I mean.
There's nothing to do with this type of random processes. No, this is quite different.
Well,
it was on the same slide.
Yes. So no, I mean it's a similar type of random process, but it's certainly different than this process that we use now here at the end. So they also somehow partition their trees into the two partition classes, and then you do different things for the partition classes. But that's rather natural in that settings, because yeah. So you need to somehow control the edges.
And it is true that such a graceful packing exists for random tree.
Yes, so that, I mean, so since they can go with their process, because they also kind of then use these more modern techniques to control dependencies, they can go up to maximum degree n over log n, so therefore they get random trees, yes.
But they are doing near graceful.
Near graceful, also near graceful. Yeah, no, I mean, I think graceful, nothing is known. I mean, really graceful. No, they are really just these banana tree results.
Okay, any other questions? That's not a question, right? So, well, let's thank the speaker again.